Chapter 3, Runway Design. You can download a PDF on airport planning and design from the link given below in playlist Airport Planning and Design. The Chapter 3, Runway Design covers general airport layout, basic patterns of runway, analysis of wind data by Windows diagram, length of runway, that is correction to runway length by ICAO and FAA specification, and runway geometric design. The Chapter 3 runway designs covers in 6 hours. General. A runway is a rectangular area on the airport surface prepared for the takeoff and landing of aircraft. An airport may have one runway or several runways which are sited, oriented and configured in a manner to provide for the safe and efficient use of airport under a variety of conditions. Airport layout and its components. Layout of an airport is dependent upon a number of factors. The most important are number and orientation of runways, number of taxiways, size and shape of aprons, the area and shape of the land, topography and site soil condition, obstacle to air navigation, require proximity of land usage within the airport boundary, surrounding land uses, timing and scale of phased development of airport, and meteorology. Size and scale of airport facilities being planned. The component of airport layout are as follows. The first component is airfield, consisting landing strip, runways, shoulder and taxiways, stopways, aprons, etc. Terminal area, gates, terminal buildings, aircraft service facilities, flight support area consisting of structures and facilities for air traffic control, navigational aids, fueling the aircraft, etc. This is the picture showing the basic component of aircraft, the basic component of airport and simply layout of airport. This is the service road, and from service road we enter to the airport area, that is from the approach road. Then the vehicle park the vehicle and enter to terminal building for the airport service, flight service, checkout and services. And this is the apron and turf, taxiway and runway. Factors affecting runway orientation. Wind. The major factors that affect the orientation of runway is the wind. Runway are oriented along the direction of prevailing wind direction. Airspace availability. Environmental factors like noise, air and water quality. Obstruction to navigation. Air traffic control visibility. Wildlife hazards. Terrain and soil consideration. Nature and man-made obstruction. Runway configurations. This is the figure showing the single runway. And this is the parallel runway. In this case, an aircraft takeoff from, suppose runway A takeoff, an aircraft takeoff from the runway, and it requires minimum 2 seconds to take off an aircraft from the runway B, so that they can be laterally and vertically separated for the safe operations of aircraft in space. Similarly, these are the intersecting runways. Similarly, open V runways. Windows diagram. It is the graphical representation of wind data, direction, and intensity. Data should be collected for the period of 5 to 10 years. The appropriate orientation of runway or runways at an airport can be determined through graphical vector analysis using a wind roads. Generally oriented in the direction of prevailing wind, headwind. Direction of wind opposite to the direction of landing and takeoff. This headwind provides both advantages for the takeoff as well as landing. In case of takeoff, headwind provides greater lift on the wings, thus shorter length of runway is enough. And in landing case, headwind provides a braking effect and aircraft comes to stop in a smaller length of runway. If landing and takeoff are done along the wind direction, it may require longer runway length. It is not possible to obtain the wind direction along the direction of runway. So for example, in this case, this is a certain intensity of wind blowing at airport at an angle of theta with center line of runway. Then there is two component, that is a p sine theta component and p cos component theta. Here p cos theta is the component of wind along the direction of runway, that is taken as the headwind. And similarly, v sine theta component is the perpendicular to the runway, and this component v sine theta that is perpendicular to the runway is called the crosswind component. The summation of all crosswind component are limited for specific aircraft. For example, for small aircraft, the crosswind component must be less than 15 kilometers per hour. For mixed air traffic, the sum of all crosswind component must be less than 25 kilometers per hour. For big aircraft recommended by ICAO, the crosswind component must be less than 35 kilometers per hour. Wind coverage. The percentage of time in a year during which the crosswind component remains within the limit is called wind coverage. FAA recommends for a mixed air traffic, wind coverage should be 95% with the limit of 25 km per hour crosswind component. For busy airport, wind coverage must be 95 to 100%. There are two types of windows diagram used for the determination of runway orientations, that is method 1 or type 1 and type 2. In case of type 1, absence of wind data not account for a crosswind component. There is no consideration of crosswind component in method 1. Similarly, in method 1 is not so accurate, and in method 1 the radial line represents the wind directions and frequency of wind is marked on a radial line scaled. Plotted points are joined by the straight line. The best runway orientation is the longest line on Windows diagram. And similarly, in type 2 or method 2 of Windows diagram, wind data is necessary and direction, duration and intensity are also required. Circle represented the wind velocity, radial line represent the wind direction, and percentage of frequency, that is plotted on appropriate segment, and velocity less than 6.4 kilometers per hour is taken as calm period, and separate circle, that is the calm period. Windows type 1. It is a graphical representation of wind data, direction and intensity. Data should be collected for the period of 5 to 10 years. Wind data average of 8 years period is given below, and this is the example. In this example, the percentage of different intensity of wind is categorized into three classes, that is 6.4 to 25 kilometers per hour, 25 to 40 kilometers per hour, 40 to 60 kilometers per hour, and in 16 direction individual percentage of intensity of wind is given in table below. And this and from Windows diagram type first we determine the best alignment of runway, that is the best orientation of runway. For this case we need first in 16 direction and total sum, that is the uh, for north direction that is 6.5 6.4 to 25 kilometers, that is 7.4 percentage, and 25 to 40 kilometer per hour 2.7, and 40 to 60 kilometer per hour is 0.2 percentage, and total percentage of wind blowing in the north direction equal to 10.3. And we need the total sum of the percentage in individual 16 direction and is calculated as table. And then we divide the direction north south east direction in 16 direction as in given in figure. Then point out the highest value in the sum, and in this case the point highest value is 14.3, and scale these radial lines, and in this case we scale this radial line by the multiple of 5, that is this circle represent a 5 percentage. Similarly this circle represent the 10 percentage, and this circle represent the 15 percentage of total wind in individual direction. After then we plot the summation of total sum percentage in individual direction, that is in north direction total is 10.3, that is in north direction 10.3 data is plotted. Similarly all these 16 data is plotted in individual direction as shown in given figures. As the total sum is plotted in individual direction, then we connect the line with straight line, and this is the Windows diagram. In Windows diagram type first, the best runway orientation is the maximum line, that is the longest line in the Windows diagram. In this case the longest line is along the direction of north south or south north direction, hence the best appropriate orientation of runway is north south direction. And in this case the uh, total sum of the percentage considered equals to 86.5 percentage. Therefore 100 minus 86.5, that is 13.3 percentage of the time wind intensity is less than 6.4 kilometers, that is the calm period. And in this case the best runway orientation is north south direction. Similarly Windows diagram type 2, the Windows procedure makes use of transparent template on which three parallel lines have been plotted. The middle line represents the center runway center line, and the distance between it and each of the outside line is equal to the crosswind component. And this is the 16 direction of the wind considered as in previous, and this is a transparent template. And this is the typical wind data to determine the best runway orientations by Windows type 2. In this case the individual wind intensity and percentage are plotted in respective segment. Therefore first the north south east direction is divided into 16 direction, and in these directions mark the circle of 6.4 km per hour, and this is the circle representing the intensity of 6.4 kilometers from the center line. And similarly this is the circle representing the scaled value of 15 kilometers from the center. Similarly, this is the 30 kilometer per hour scaled from the center of from the center. And similarly, this is the circle representing the scaled value of 47 kilometer per hour. In this case, the Windows diagram type 2, the respective value is plotted on respective segment. That is in 6.4 to 15 kilometer segment. That is, this is the 6.4 kilometer circle, and this is the 15 kilometer per hour circle. And in the north direction, 3.6 is plotted on respective segment. That is, this is the segment representing the north directions, and 6.5 to 15 km per hour segment. Then is these 16 data are plotted on these 16 segment of 6.4 to 15 km per hour and is plotted as in figure. And similarly, this 15 kilometer circle and 30 kilometer circle, each segment is plotted with each values given in table and is plotted as shown in figure. And similarly, this is the circle scaled of 30 kilometers per hour, and this is the circle scaled of 47 kilometers per hour, and each segmented value is plotted on its respective segment and is plotted as shown in figure. In this case, the segment, this segment represents the 0 percentage, that is a nil area, and this is the segment represent this whole segment is represented by 0.4 percentage, for example. And this is the segment, between 6.4 to 15 km per hour. This is the area that represents the total percentage, 8 percentage. And similarly, this is the segmented between 15 to 30 kilometers per hour. This is the whole area is represented as 0.7 percentage. And similarly, this is the segmented between 30 kilometer to 47 kilometer per hour, and this whole area, is represented by 0.3 percentage. And in Windows type 2, we make a transparent template whose scaled whose width is scaled to 15 km per hour from the center line up and down. That is a total width of the transparent template is taken as 30 km per hour. The width of the template is taken as a first range, that is a 6.4 to 15 km per hour. Hence the template is taken width of the template is taken as the 15 width of template is taken as 15, scale value of 15 from the center left to and center right, and total width of the template is taken as 30 kilometer per hour value. In this case, this template is laid over this direction map, and the total percentage covered by this template is sum, and the total sum of the individual number of trials is taken, and the maximum value of the percentage is taken as the best runway orientation. And for example, and this is the trial first. In this trial, the total area covered by this template is sum up. In this case, the whole area is taken as 0.7 percentage, and only partial occupancy of the segment is shown in figures, and this is taken as, and this is accurately calculated from the graphical method. And in this case, for trial 1, the total sum of the percentage occupied by this transparent template is taken as x. And similarly, this is the trial 2 along direction of north south direction, and the total sum of the area covered by this template is taken as sum y. Similar for trial 3, the total sum of the percentage covered by this template is taken as sum z. And similarly, For n number of trial, we align the template from north south east west directions, and for east west direction there will be the maximum percentage of the value covered by the this template and is taken as m, and m will be the maximum value. Since the values are along the north south direction, not east sorry, the this east west direction of a template cover the maximum percentage of wind data. Since the data is aligned in not aligned in east west directions, that is the best runner alignment will be the north west east west direction. And the total sum will give the 95 percentage, that is greater than 95 percentage, that is the available wind coverage will be 95 percentage and is greater than 95 percentage, which is okay as per recommended by FAA. Basic runway length. It is the length of the runway under the following standard condition. The first standard condition is the airport altitude is at sea level. That is the standard condition for the basic runway length determination is sea level. That is elevation is 0 meter. Airport temperature is 15 degrees Celsius. That is the if the airport is in sea level, the standard temperature will be 15 degree Celsius. Runway is level in longitudinal direction. That is the longitudinal slope will be the 0. No wind is blowing on runway, and the aircraft is loaded with its full capacity. Declared distances in runway. And this is the figure showing the L section of runway, and this is the plan section of runway. Their point A is the starting point of the runway, and B is the point representing the velocity p1 as the distance speed, and point C representing the velocity via, that is rotational speed, and the point D representing the speed v LOF, that is the lift off speed, and X, Y, Z, and at the point Z the aircraft will be 35 feet above the ground, and at that respective point of velocity will be v2, that is takeoff safety speed. In this case, the aircraft can run to up to x distance. Up to x distance can be run to x distance for the takeoff, and the distance from A to X is taken as takeoff run available, and distance A to X, A to Y is the accelerated stop distance available. In this case, if the aircraft is ready for takeoff and is speeding up to point B, that is the aircraft gains a distance speed. If a pilot notice the failure in sudden failure in aircraft, and he has to stop the aircraft up to y distance, that is why up to A to Y the distance is taken as accelerated stop distance available. And when the aircraft is take off and gains a height of 35 feet from a ground, and up to respective distance is taken as the takeoff distance available. Correction for elevation, temperature and gradient. Since airport cannot be constructed in standard conditions, that is standard elevation, standard temperature and standard gradient, there should be correction for the elevations, temperature and gradient which are constructed or designed on different than standard condition. First, correction for elevations. ICAO recommends that the basic runway length should be increased at the rate of 7% per 300-meter rise in elevations above the sea level. That is, if the runway is constructed above certain elevation, the basic length of runway is increased at the rate of 7% per 300-meter rise in elevation. Second correction is the correction for temperature. ICAO recommends that the basic length of runway after having corrected for elevation should be further increased at a rate of 1% for every 1 degree rise of airport reference temperature above the standard atmospheric temperature TS at that elevation. The temperature gradient of the standard atmospheric from the mean sea level to the altitude at which the temperature becomes 15 degrees Celsius is minus 0.0065 degree per meter. That means the standard temperature of airport for the sea level is 15 degrees Celsius, and when the airport has to be planned or designed on suppose 100 meter elevations, the standard temperature varies and decreases at 0.0065 degrees Celsius per meter. That is the 15 degrees Celsius will not be the standard atmospheric temperature for the 100-meter elevations. That's why we have to calculate the standard atmospheric temperature and is taken as 15 degrees 15 minus 0.0065 into 100. Airport reference temperature TR is defined as the monthly mean of average daily temperature for the hottest month of the year plus one third a difference of this temperature TA and monthly mean of maximum daily temperature TM for the same month of the year. That is TR equal to airport reference temperature is the average of monthly mean temperature plus one third the difference between maximum daily temperature and the mean of average daily temperature. Check for total correction for elevation and temperature. After the basic length of runway is corrected for elevation and temperature, the next step is to check for the total correction for elevation and temperature. If the total correction, that is the elevation and temperature, exceed 35% the basic runway length, these corrections should then be checked up by conducting specific studies. Correction for gradient. ICAO doesn't recommend on this correction. FAA recommends that the runway length after having been corrected for elevation and temperature should be further increased at the rate of 20% for every 1% of effective gradient. Since the basic standard condition for the gradient is 0% gradient, as in all cases no 0% gradient runway cannot be designed or planned. That's why we have to make a correction for the gradient, and the correction is at the rate of 20% for every 1% of effective gradient. Effective gradient is defined as the maximum difference in elevations between the highest and lowest point of the runway divided by total length of the runway. Examples 3. The data below refers to the daily temperature for the hottest month of the year 1988 for a given airport site. Determine the airport reference temperature. And this is the tables given, and this is the table that shows the maximum and average daily temperature of hottest month of the year 1988, and here the mean of maximum daily temperature is taken as and calculated as 43.72 degree. Similarly, mean of average daily temperature is calculated as 22.32 degrees Celsius. Therefore, airport reference temperature TR equals to TA, that is the sum is the mean of average daily temperature plus one third of mean of maximum daily temperature and mean of average daily temperature, and calculated as airport reference temperature as 32.12 degrees Celsius. Example 4. The monthly mean temperature of the atmosphere at a particular site where an airport has to be developed are given below. Determine the airport reference temperature. And this is the temperature. Table showing the average mean of average daily and mean of maximum daily temperature of each month. Since in this case the maximum temperature that shows the hottest month is the month of June. That's why we take the mean of average daily temperature is taken as TA equals 40 degrees Celsius, and mean of maximum daily temperature, that is TM, is taken as 50 degrees Celsius. Therefore airport reference temperature is taken as and calculated as 43.33 degrees Celsius. Example 5. Find out the required runway length for the airport of reference code 4D located at for 50-meter elevation above mean sea level. The runway effective gradient is 0.5%. The monthly mean of maximum and mean daily temperature of hottest month of the year are 27 degrees Celsius and 18 degrees Celsius respectively. Since the given airport reference code is 4D and the 4D, the minimum length of the reference field length must be greater than 1800 meters. That's why we taken the length of the basic runway as 1800 meters. And for the correction for elevation, and the correction for elevation is taken as 7% per 300 meters. That is why the total correction for the elevation is taken as 1.108. That is corrected runway after elevation is calculated as 1989 meters. And similarly for temperature correction, at the standard airport reference temperature at sea level is 15 degrees Celsius, which is not same for the elevation of 450 meters. That is why at the elevation of 450 meters, the standard airport reference temperature is taken, has to be calculated, and is calculated as 15 minus 0.0065 into 450. That is calculated as 12.08 degrees Celsius. That is, at sea level the standard airport temperature is taken as 15 degrees Celsius, and at the elevation of 450 the standard airport reference is taken as calculated as 12.08 degrees Celsius. Then rise in rise in temperature is taken as 21 minus 12.08 equals to 8.92. Then the temperature correction is taken as the 1% per increase in temperature in airport reference temperature. That is rise in temperature equal to 8.92 meters, and 0.11 into 8.92 plus 1, that is the correction for the temperature is taken as 1.0892, and the corrected length for elevations and temperature, that is the corrected length of runway after elevation and temperature correction is taken as LET is calculated as 2166 meter. Now check for total correction for elevations and temperature, and is calculated as 20.33%, that is less than 35%, hence it is okay. That is our correction is correct. D. Correction for gradient, and correction for gradient is taken as 20% for every change in effective gradients, that is 20%, 0.2 per 0.5% gradient, and is taken as 1.1. That is corrected length of runway after elevation, temperature and gradient correction is calculated as 2382.6 meter. In this way we can determine the basic length of runway in standard condition as well as non-standard condition. You can download the PDF note from the link below in playlist Airport Planning and Design.